Dear students, today we will discuss about the internal and external noise in the modulation system. So, what is the internal and external noise in modulation system? So, what is the noise? Noise is electrical term may be defined as any unwanted introduction of energy tending to interfere with the proper consent reception and reproduction of transmitted signal. Noise is mainly of concern in receiving system where it set a lower limit on the size of signal that can be usefully received even when precautions are taken in eliminate noise from faulty connections or that arising from external sources. It is found that certain fundamental sources of noise are present within electronic equipment that limit the receiver's sensitivity. So, classification of noise. So, noise whose source are external to the receivers, and second one, noise created within the receiver itself. So, noise is created outside the receiver, and external noise can be further classified as first one is atmospheric noise, second one extraterrestrial noise, and third one is the industrial noise. So these are the external noise. So what is the atmospheric noise? Atmospheric noise or static is generally caused by lightning discharge in thunderstorm and other natural electrical disturbance occurring in the atmosphere. Since these processes are random in nature, it is spread over most of the RF spectrum normally used for broadcasting. Atmospheric noise consists of spurious radio signals with components distributed over a wide range of frequency. It is propagated over the earth in the same way as ordinary radio waves of same frequency, so that any point on the ground static will be received from all thunderstorm local and distant. Atmospheric noise becomes less at frequency about 30 megahertz because of two factors. One factor is that higher frequency are limited to the line of sight propagation or less than 80 kilometer or so on. Second one, nature of mechanism generating this noise is such that very little of it is created in BHA, very high frequency range and above. So that is the cosmic noise, and second one is the solar noise. So what is the solar noise? Under normal conditions, there is a constant noise radiations from sun simply because it is a large body at very high temperature over 6,000 degree centigrade on the surface. It therefore radiates over a very broad frequency spectrum, which includes frequency we use for communication. Due to constant changing nature of the sun, it undergoes cycle of peak activity from which electrical disturbances erupt, such as corona flares and sunspots. This additional noise produced from a limited portion of the sun may be higher magnitude than noise received during period of quiet sun. Next one is the cosmic noise. So source of cosmic noise are distant stars as they have very high temperature. They radiate radio frequency noise in a similar manner as our sun, and their lack of nearness is nearly compensated by their significant number. The noise received is called black body noise and distributed fairly uniformly over the entire sky. So that is the cosmic noise. Next noise is the industrial noise. So in this industrial noise, this noise range between 1 to 600 megahertz in urban, suburban, and other industrial areas and is most prominent. Source of such noise: automobiles and aircraft emissions, electric motors, switching equipment, leakage from high voltage lines, and a multitude of other heavy electrical machines. That is the industrial noise examples. The noise is produced by the arc discharge present in all these operations. This noise is most intense industrial and densely populated areas. Next one is internal noise. So noise created by any of the active or passive devices found in receiver. Such noise is generally random, impossible to treat an individual voltage basis, but easy to observe and describe statistically, statistically because the noise is randomly distributed over the entire radio spectrum. Therefore, it is proportional to bandwidth over which it is measured. So, internal noise can be further classified as: first one is thermal noise, next one sound noise, and third one is the low frequency or linear noise. So these are the internal noise. What is the thermal noise? The noise generated in a resistance or a resistive component is random and is referred to as thermal agitation, White or Johnson noise. What is the cause of this noise? The free electrons within a electrical conductor possess kinetic energy as a result of heat exchange between the conductor and its surroundings. Due to this kinetic energy, the electrons are in motion. This motion is random through collision with imperfection in the structure of the conductor. This process occurs in all real conductors and gives rise to conductor's resistance. As a result, the electron density throughout the conductor varies, randomly giving rise to randomly vary voltage across the ends of conductor. Such voltage can be observed as a flicker on a very sensitive voltmeter. So the average or means noise voltage across the conductor is zero, but the root mean square value is finite and can be measured. The mean square value of the noise voltage is proportional to the resistance of the conductor, to its absolute temperature, to the frequency bandwidth of the device measuring the noise. The mean square voltage measured on the meter is found to be En square equal to 4 RKTPN. So where En root mean square noise voltage in volt, and R is the resistance of the conductor, and T is the temperature in Kelvin. Dn is the noise bandwidth in hertz, and also K is the Boltzmann constant, which has the value of 1.38 into 10 to the power minus 23 joule per Kelvin. At the RMS noise voltage is given by En equal to under root of 4 RK TdN. Also note here, thermal noise is not a free source of energy. To abstract the noise power, the resistance R is to be connected to a resistive noise, and in thermal equilibrium, the load will supply as much energy to R as its receivers. In this circuit diagram, in analogy with any electrical source, the available average power is defined as the maximum average power the source can deliver. Consider a generator of EMF, electromagnetic field, En volt and internal resistance R in this figure, assuming that RL is noiseless and receiving the maximum noise power generated by R. So under these conditions of maximum power transfer, RL must be equal to R, then Pn noise power will be equal to B square upon Rn or equal to B square upon R, and also En upon 2 ka whole square upon R, and that is the equal to En square upon 4R. Using this equation, the noise power Pn equal to KTBN. So there is an example in which given different data, and we can find out the with the help of these given data the noise power, and the thermal noise property of a resistor are may be represented with the equivalent volt generators, and equivalent current generator is found using the Norton theorem. Using conductance G equal to 1 upon R, the RMS noise current is given by IN square equal to 4G KTBN, where G equal to 1 upon R, that is the conductance. Let R series represent the total resistance of the series chain, where R series equal to R1 plus R2 and so on. So in that case, put the value of this series resistance in this equation will be En square equal to 4R1 plus R2 plus R3 and so on KTBN, and also En square equal to En1 square plus En2 square and plus so on. Hence the noise voltage of the series chain is given by En equal to under root of En1 square plus En2 square and so on. What in the case of parallel resistance? With resistance in parallel, it is best to work in term of conductance. Let G parallel represent the parallel combination of conductance, where G parallel equal to G1 plus G2 plus G3 and so on. So in that case, In square equal to 4G parallel KTBN, and put here the value of G parallel. So this equation In square equal to 4 into G1 G2 plus G3 into KTBN, and also In square equal to in1 square plus in2 square and plus so on. Reactants do not generate thermal noise. This follows from the fact that reactants cannot dissipate power. Consider an inductive or capacitive reactance connected in parallel with a resistor in this figure. In thermal equilibrium, equal amounts of power must be exchanged, that is P equal to P2. But since the reactants cannot dissipate power, the power P2 must be zero and hence P1 must also be zero. Next one is the soot noise. Soot noise is random fluctuation that accompanies many direct current crossing proportional and crossing potential barrier. The effect occurs because the carriers, electrons, and holes in semiconductors do not cross the barrier simultaneously, but rather than random distribution in the timing of each carrier, which gives rise to random component of current superimposed on the steady current. In case of bipolar junction transistor, the bias current crossing the forward bias emitter base junction carries the soot noise. When amplified, this noise sound as a though a shower of lead salt were falling on a metal sheet, hence the name soot noise. Although it is always present, soot noise is not normally observed during measurement of direct current because it is small compared to it does contribute significantly to the noise in amplifier. The means square noise temperature is proportional to the DC flowing and most device the mean square soot noise is given by IN square equal to 2 IDC EBN square ampere, where IDC is the direct current and amperes and Q is the magnitude of the electronic charge and BN is the equivalent noise bandwidth in hertz. Next one is the flicker noise. So this noise is observed below frequencies of few kilohertz and its spectral density increase with decrease in frequency. For this reason, it is sometimes referred to as a 1 upon f noise. The cause of flicker noise are not well understood and is recognizable by its frequency dependence. Flicker noise becomes significant at frequency lower than about 100 Hz. Flicker noise can be reduced significantly by using wire bound or metallic film resistor rather than the more common carbon composition type. In semiconductors, flicker noise arises from fluctuation in the carrier densities, hole and electrons, which in turn give rise to fluctuation in the conductivity of the material. The noise voltage will be developed whenever direct current flows through the semiconductor and the mean square voltage will be proportional to the square of the direct current. In electronic device, it shows up as a flow frequency phenomena as the higher frequencies over set down by white noise from other sources. What noise? It consists of sudden step like transition between between two or more discrete voltage or current levels as high as several hundred microvolt at random and unpredictable times. Each shift in offset voltage and current often lasts from several milliseconds to seconds and sounds like popcorn popping is hooked up to an audio speaker. The most commonly invoked cause is the random trapping and release of charge carriers at thin film interface or a defect sites in bulk semiconductor cluster. In case where these charges have a significant impact on transistor performance such as under and MOS gate or a bipolar based region. The output signal can be substantial. These defects can be caused by manufacturing process such as heavy oil implantation. So here in this figure, typical of a noise showing discrete levels of channels, current modulation due to the trapping and release of the single carrier for three different noise conditions. Spectral density. So what is the spectral density? Spectral density is power distribution in frequency spectrum. It used to dis- differentiate type of noise, plot of light intensity power as a function of frequency of wavelength. Thermal noise lies in category of power signal has spectral density. Bn is property of external receiving system and Bn assumed flat. So from equation Tn equal to En square upon 4R equal to 4R KTBn upon 2R equal to KTBn, and since E n square equal to 4R KTBn where En RMS noise voltage, R equal to resistance of conductor, Vn is the noise bandwidth in hertz, and K is the Boltzmann constant, and T is conductor temperature in Kelvin. So spectral density for mean square voltage is given by the GEF equal to En square upon Vn equal to 480 upon into V square per hertz, since En square equal to 4R KTVN. Spectral density are flat, that is independent of frequency, as shown in this figure below. There are spectral density versus thermal noise spectral density. So thermal noise is also called white noise because of analogy to white light that has flat spectrum means signal contain equal power within a fixed bandwidth at any center frequency. When white noise is passed through a network, then spectral density is changed by shape of network frequency response. Total noise power at output is sum of the noise contribution over complete frequency range, taking into account of frequency response shape. So in this figure, consider a power spectral density response in below figures. In this figure, at frequency f1, the noise power for small band width delta f about f1 is delta Tn1 equal to Sp f1 into delta f. Here delta f assume flat about f1, and so noise power is equal to area of shaded strip about F1 similar for F2, F3, so on. That power is sum of all these small areas equal to total area under the curve. So area of the curve gives total mean square voltage. So integration of GAF for the frequency 0 to infinity, that is the area of curve, and equivalent noise bandwidth. It is the frequency span of a noise power curve with amplitude equal to actual peak value at this same integrated area. If R is connected to input of LC filter as in figure A, this represents an input generator of mean square voltage spectral density 4 RKT feeding a network of R and LC filter. Let's transfer function of network including RBHF. So spectral density for mean square voltage is 4 RKT HF whole square. HF is the ratio of output to input voltage for mean square voltage. So that is the HF versus frequency graph in this figure. So total mean square output voltage is given by Vn square equal to integration of 4 RKT into HF whole square df, where f equal to 0 to infinite. So total mean square voltage at the output can be stated as Vn square equal to 4 RKT Vn by above two equation gets equivalent noise bandwidth of the network. So Vn bandwidth equal to integration of HF square delta F or equal to area under curve of HF whole square for frequency 0 to infinite. So in this example, consider in figure below input capacitance of the voltmeter. You measure the noise voltage across a circuit diagram. So here RC network and its transfer function used to determining noise bandwidth. Transfer function of RC network HF equal to 1 upon 1 plus omega CR under root. Equivalence noise bandwidth of the RC network is BM integration of HF into 2DF equal to 1 upon 4 RC and F equal to 0 to infinite. So Vn square equal to 4 kT x1 upon 4 RC equal to kT upon C. So mean square voltage originates from resistance R even though it is independent of resistance and inversely proportional to capacitance even though C does not generate noise. Transfer function HF equal to XC upon ZS, where ZS equal to R into 1 plus J Y Q is impedance of the series tuned circuit and XC equal to 1 upon J omega C or reactance of capacitor. So mean square noise voltage is Bn square equal to 4 RKTBn and use of the relation Q square R equal to RD and F equal to 0 to infinite and then Bn equal to 1 upon 4 RDC. RD is the dynamic resistance of the tuned circuit. Noise bandwidth expressed as a function of 3 decibel bandwidth of circuit. So from equation bandwidth 3 dB equal to F naught upon Q and RD equal to Q upon omega naught C combined the equation gets Dn equal to mean square voltage at the output as Vn square Rd Ktx1 upon 4 Rd C equal to Kt upon C. So bandwidth Vn is the bandwidth here, and here assume that Q factor is constant and independent of frequency. For end result give good indication of noise expected in practice, but not true for ranging 0 to infinity. In radio receivers, noise is generated at antenna receivers input and output noise bandwidth is determined by the audio part of the receiver. So equivalent noise bandwidth equal to area of normalized frequency curve for low frequency section. Normalized means curve maximum value is unity and response curve show output in decibel relative to maximum as in next figure. So equivalent noise bandwidth is area of curve for a single sideband type. Then noise bandwidth appears on both sides of the carrier and gets double. There are different response curve. First response curve is the amplifier frequency response curve, and B is the curve of using A linear scales, and C is the noise bandwidth of a double sideband receivers. Next, signal to noise ratio or S and R ratio. In communication, it is the signal to noise absolute value of noise. It is defined as a power ratio S upon equal to PS upon PN or equal to PS square upon BN square. So repeaters or amplifier insert to make up for the loss in analog telephone cables. If power loss of a line section is L, then repeaters amplifiers power gain G is chosen. So Lg equal to one long line divided into identical section. If input signal power equal to PS to first section, a signal passes along the length power. Each repeater is PS since Lg equal to 1 for each link, but noise power are additive and the total noise at the output of mth link is Pn equal to Pn1 plus Pn2 plus Pn3 and so on. So if each link are identical and contribute Pn, then total noise power is Pnm equal to Npn, then output signal to noise ratio is S upon N, output signal to noise ratio, and dB equal to 10 log of PS upon Npn or equal to S upon N1 decibel in dB, where S upon N1 is the ratio for one link and N decibel is number of links expressed as power ratio in decibels. Next one is the noise factor. So what is the noise factor? Noise factor is the ratio of available signal to noise ratio at the input to the available signal to noise ratio in the output. Consider a signal source at room temperature T naught equal to 290 Kelvin, providing an input to an amplifier. The available noise power from this would be Pni equal to Kt naught Bn, where K is the Boltzmann constant and Bn is the equivalent noise bandwidth in Hertz. So these are the available output signal to noise ratio will be less than that at the input in these figures. And noise factor F defined as F equal to available signal to noise power ratio with the input divided by available signal to noise power ratio at the out. So F equal to PSI upon KT naught Bn into P naught Pn naught upon GPSI. So F equal to Pn naught upon Gk naught Bn. It follows from this that the available output noise power is given by Pn naught equal to Fkgt naught Bn. F can be interpreted as the factor by which the amplifier increase the output noise. For if amplifier were noiseless, the output noise would be GKTB, and the available output power depend on the actual input power delivered to the amplifier. So noise factor is a measured quantity and will be specified for a given amplifier or network. It is usually specified in decibel when it is referred to as the noise figure. Thus, noise figure equal to F decibel or equal to 10 log of F. So for this is the example for calculation of the signal to noise ratio, in which figure of noise is given here also, and signal to noise ratio also given here. So we find out the signal to output noise ratio. Amplifier input noise in term of F. Amplifier noise is generated in many components throughout the amplifier. What it proved convenient to imagine it to originate from some equivalent power source with the input of the amplifier. The total available power input noise is then Pn I equal to Pn naught upon G equal to F kt naught, and power k P naught Bn, and hence the amplifier must contribute Pna, where Pna equal to F kt naught Bn minus kt naught Bn, or also F minus 1 into kt naught Bn. So this is the Pna. Next, noise factor of amplifiers in cascade. So consider first two amplifier in cascade. The problem is to determine the overall noise factor and in terms of individual noise factors and available power gains. The available noise power and output of the amplifier one is P and naught 1 equal to F1 G1 KT naught Bn, and this available to amplifier 2. So amplifier 2 has noise F2 minus F1 KT naught Bn of its own. It is input, hence total available noise power at the input of terminal amplifier 2 is Pn I2 equal to F1 G1 KT naught Bn plus F2 minus 1 into KT naught Bn, and if Pn naught equal to G2 Pn I2, in that case G2 into F1 G1 KT naught Bn plus F2 minus 1 KT naught Bn. The overall available power of the two amplifier in cascade is G equal to G1 into G2, and that's overall noise factor we have, then output noise power can be also expressed as Pn naught equal to Fg T naught Pn, and also in term of noise figure, the F1 G1 KT naught Pn plus F2 minus 1 KT naught Pn equal to Fj KT naught Pn, and F1 G1 plus F2 minus 1 equal to Fg, and F also F1 G1 upon G plus F2 minus 1 upon G, where G equal to G1 into G2. So noise figure F equal to F1 plus F2 minus 1 upon G1. This equation shows the importance of high gain low noise amplifier as the first stage of a cascaded system. By making G1 large, the noise contribution of the second stage can be made negligibly, and F1 must also be small so that the noise contribution of the first amplifier is low. So F equal to F1, F2 minus F1 upon G1, F3 minus 1 upon G1, G2. This is known as the noise of figure. These are two particular situations where a low noise front end amplifier is employed to reduce the noise. One of these is in satellite receiving system. The other is in radio receiver used in pickup weak signals such as short wave receivers. In most receivers, a stage known as the mixer stage is employed to change the frequency of the incoming signal, and it is known that mixer stage have notoriously high noise factors. By inserting an RF amplifier ahead of the mixer, the effect of the mixer noise can be reduced to negligible levels. This is illustrated in the following examples. So, these are the examples in which we calculate the overall noise figure referred to the input by the different given parameters. And next one is the noise temperature. The concept of noise temperature is based on available noise power equation Pn equal to KTB, and here the subscript has been included to indicate the noise temperature is associated only with available noise power. In general, TA will not be same as the physical temperature of the noise source. As an example, an antenna pointed at deep space will pick up a small amount of cosmic noise. The equivalent noise temperature of antenna that represent this noise power may be a few tens of kelvins. Well below the at the sun, physically ambient temperature of the antenna. If the antenna is directly pointed at the sun, the received noise power increase enormously, and the corresponding equivalent noise temperature is well above the ambient temperature. When the concept is applied to an amplifier, it related to equivalent noise of the amplifier referred to the input. If the amplifier noise referred to the input is denoted by PNA, the equivalent noise temperature of the amplifier referred to the input is TE equal to PNA upon KVN, where PNA equal to F minus 1 KT naught PN, and we get equivalent noise temperature of the amplifier as TE equal to F minus 1 upon TA. So this shows the proportionality between TA and F. So these are the two reference books for this topic. One is the analog communication by Bhatt et al. Second one is the digital communication by T.L. Singer. And there are some multi-choice questions here. So, question first, transit time noise is A, low frequency noise, option B, high frequency noise, option C, due to random behavior of carrier charge, option D, due to the increase in reverse current in the device. So, here the correct answer option B, transit time noise is high frequency noise. Next question, noise, the figure of merit. Gamma is ratio of output signal to noise ratio to input signal to noise ratio. Option B, ratio of input signal to noise ratio to output signal to noise ratio. Option C, ratio of output signal to input signal to a system. Option D, ratio of a input signal to output signal to a system. So here correct answer is option A. Next question, the noise voltage Vn and the signal bandwidth B are rated as option A, Vn is directly proportional to bandwidth. Option B, Vn is directly proportional to under root bandwidth. Option C, Bn is the inversely proportional to the absolute temperature. Option D, Bn is the inversely proportional to the bandwidth. So here correct answer is option B. Bn is directly proportional to the under root bandwidth. So there are some other multi-choice question here. Thank you. Thank you very much.